A very good afternoon to all the participants and our distinguished speaker. I am Rishma Kadam. I, on behalf of SAP CRNTS IIT Bombay, take this opportunity to welcome you all for today's talk on ICP-AES, which will be presented by Mr. Olaf Schulz. Before we proceed, I would request the head of SAP CRNTS, Professor Suparna Mukherjee, to give us an overview of SAP IIT Bombay. Over to you, ma'am.
Thank you, Reshma.
Thank you, ma'am.
Yeah, I welcome all of you to this webinar, and I would like to make a brief presentation. I'd like to share my screen now. So, SIFE and CRNTS is a facility where we have various sophisticated analytical instruments. So, it was first started with DST support in 1976 as SIFE. And then we formed CRNTS in 2005. And subsequently, the two were merged together in 2008. And subsequently, we have several major instrumental facilities in SIFE, and there are some in CRNTS also. And under CRNTS, we have PhD students working in the center, and they are guided by faculty members across the institute. And as you can see, we have a large number of users, more than 1,700, and about 13,000 samples were run during the financial year 21-22. These are some of the facilities that we have in SIFE IIT Bombay. We have electron microscopy facilities, the FEGTIM, FEGSIM, and dual beam FIB, FEGSIM. In addition, we have several mass spectroscopy facilities coupled with GC. So we have HRGCMS. We also have high-resolution liquid chromatography, both Orbitrap and QTOF. And in addition, we also have ICP-MS and TOF SIMS. And there are various other instruments that are there in the center inside. This includes CHNSO analyzer, ESR, then FTIR, NMR, SACS, and profilometer. And we also now have more recently several thermal analysis instruments. Now, in addition to the SIFE facilities, we have several central facilities located in SIFE CRNTS, which are listed here. And ICP-AES is one of these central facilities located in SIFE. And this is a very old facility we had it installed in 2009. And in addition to that, we have several other central facilities like LRS, ESIM, and FECTEM 200 kV, and 2D gas chromatograph with MS detector, and UV spectrophotometer. So this is showing the number of samples analyzed all over India in 21-22. And you can see that it's not just Maharashtra. Samples come from all over India. And these are the staff members of SIFE CRNTS who actually work tirelessly to analyze the samples that are received. We receive numerous visitors from all over. And we also conduct webinars from time to time on various facilities and the applications of these facilities. And these are available in our YouTube channel also. You can join us on LinkedIn at SIFE IIT Bombay. Now, today we will be having this webinar on ICP-AES facility in CRNTS, as I mentioned. So with that, I would like to end, and we will go on to the webinar on ICP-OES on simultaneous and cost-effective multi-elemental analysis.
Thank you, ma'am, for presenting the information about all the current facilities at SAP IIT Bombay. Thank you so much, ma'am. Now, I would like to introduce our speaker, Mr. Olaf Schulz. Mr. Olaf Schulz is the product manager for ICP-OES and is responsible for the strategic development of the complete product line, including application development and product support. Mr. Olaf has experience of over 30 years in optical emission spectroscopy for material analysis and testing. Now I take this opportunity of requesting Mr. Olaf Schulz to present his slides to everyone. But before this, I would request all the participants to post their queries related to today's talk in question and answers box, which will be answered at the end of the webinar. Over to you, Mr. Olaf Schulz.
Thank you very much, Reshma. Okay, so let's start. I amended the title a little. I mean, certainly analysis needs to be efficient, but here we also talk about research. And so I thought, well, any analysis we do, and certainly ICP-OES technology needs to support research. And this is how I changed my title a little, how state-of-the-art ICP-OES technology supports your research. Now, where's my mouse? Here we go. Okay, now it works. Well, elemental analysis in research can really be a challenging task. The applications are diverse and demand the determination of major, minor, and trace elements in really a wide range of substances, from inorganic to organic matrices to complex and line-rich components. For common ICP optical emission spectrometers, this can be really a challenging task. And since not all requirements can be equally met, often several instruments need to be used to master all tasks. However, new state-of-the-art technologies let the instrument adapt to specific requirements without compromises, allowing really for the highest possible performance in every respect. And so over the next 45 minutes, I would like to present those technologies, the benefit for the user, and demonstrate the instrument's performance for several applications. Now, for an ICP in research, high performance really means a flexible sample introduction, optimal for the analytical task, multiple plasma viewing options to cater for different sensitivity requirements, certainly a powerful generator to handle higher matrix loads, a simultaneous measuring wide range, high resolution optical system, really without any drift and low stray light levels, a dynamic range detection system combined with a fast readout, and last but not least, also a modern software which supports all the flexibility. The picture you see here on this slide shows the detectable elemental scope for the ICP-OES, including the primary emission lines and the achievable limits of detection using axial plasma observation. With PBB values for the majority of the 75 elements that can be analyzed. And while most of the elements have their primary emission line in the 200 to 400 nanometer wavelength range, the alkali metals require the visible spectral range, whereas certain metals, non-metals, and the halogens require access to the UV and the VUV spectral range. So today, ICP-OES commonly uses these shell optical systems, which were originally developed and used for applications in astronomy, since despite their compact design, high resolution and a broad wavelength range are really the main characteristics. They typically use a rather low ruling density grating. The ruled grating is placed, optimized for higher incidence angles. And for this reason, it can be used at higher diffraction orders. The diffraction produces multiple overlapping orders. And since this overlap is not really useful for measurement, a second dispersive element, a grating or a prism mounted perpendicular to the dispersion level, a cross disperser or order separator is placed into the light path. Now, the resulting spectrum consists of a stack of stripes with different but slightly overlapping wavelength ranges imaged onto a plane surface. The typical trapezoid shape is caused by the fact that the different orders are shifted against each other, and the image is limited really by the size of the cross disperser. And it's really this imaging on a flat surface, which with the advent of the CCD detectors in the mid-1990s, helped the rapid expansion of this optical concept. Now, as with all optical designs, there are advantages and disadvantages. And for shell optical systems, one could summarize the advantages as a good performance in a small package. Depending on the design, the systems offer simultaneous measurement of the emission spectrum and really a good resolution in the 200 nanometer wavelength range. To achieve low dark current noise, the two-dimensional detectors are typically sub-zero cooled, and combined with a good quantum efficiency, really good sensitivities are achievable. And so for the main application of ICP-OES being the determination of toxic metals in environmental samples, shell optical systems really fulfill their task. However, optical systems are compromises, and so by design, there are also disadvantages. A shell optical system used with ICP-OES are really notoriously weak in the wavelength range below 200 nanometers. And this is the result of the prism used as a cross disperser. Even when glass with higher transparency is used, it is the thickness of the material which strongly influences absorption. An option would be to use a grating instead of a prism. This would certainly improve the capabilities in the below 200 nanometer range, however, at the expense of overall efficiency. To operate below 200 nanometers today, shell optical systems are typically purged with an inert gas. Commonly, argon or nitrogen is used. The purge gas also helps the protection of the optical components, as well as the sub-zero cooled detector from ambient influences and humidity. And since this purge is constant, even if the instrument is in standby, it affects operational costs. Another weak point is the strongly wavelength-dependent resolution. Shells only display a high resolution in higher diffraction orders, and those are not available for the wavelength range above 250 nanometers, however. And while this is not so relevant for environmental work, applications with line-rich metal matrices are problematic, since a number of important elements have their most prominent emission lines in the spectral range above 250 nanometers. And lastly, a common problem with shell optical systems is that order separation is not always complete. And this means that higher order spectra may appear in the lower order spectrum in addition. And again, while this may be unproblematic for common environmental work, line-rich applications are challenged by this effect with higher probabilities for interferences. So to summarize, shell optical systems fulfill some requirements, but may not be the best choice for special needs. Now, Paschen-Runge optical systems, in contrast, are constructed more simplistic. This design was initially invented by Henry Rowland at the end of the 19th century. And by using a concave grating, light is dispersed, but the image of the entrance slit is also focused on a circular path, provided all optical components are mounted on a circle and the focal length of the grating equals the diameter of the circle. Now, this enables fully simultaneous detection over a wide wavelength range. As the system does not require any transmission optical components, also the UV and the VUV spectral ranges are accessible. Now, Paschen-Runge optical systems are typically operated in the first and second diffraction order, and a main characteristic is that the resolution is rather uniform over a wide wavelength range. Initially, this design was used with photomultiplier tubes, and with the advent of CCD detectors, this concept, which was really dominant at the time, was abandoned, since the even surface detectors could not really be fitted to the focal curve. And this only changed when we developed a circular optic using multiple spatially fitted linear detectors in 1999. Today, this design has now been further enhanced. So the further developed design is called ORCA, and this is used by Spectro. It includes 3 individual polychromators merged into a single optical system. Using 2 entrance slit and a 3rd virtual slit, the light from the plasma illuminates all gratings and thus enables simultaneous detection of all wavelengths between 130 and 460 nanometers, plus the alkali elements up to 770 nanometers. For the light detection, 32 CMOS line array detectors are used. The separation into 3 ranges allows for maximum wavelength coverage, while maintaining high sensitivity, including the UV and the VUV spectral range, and a high resolution over the entire wavelength range. The optic itself is a hollow section cast design, which functions as an optical bench as well as a chamber. And to ensure the integrity of the optic atmosphere, the optical system uses UV+, which provides a quasi 100% availability and does not require any purge gases. Thanks to the novel detection system, the optical system does also not require sub-zero cooling, but is stabilized at 15 degrees Celsius. Construction, the hermetic sealing, and the full environmental control enable really highest wavelength stability. And this example here demonstrates this really nicely. Peak overlays for manganese at 259 nanometers over a period of 6 months show really absolutely no drift. And even also here over a 24-hour period, all elements remain in the same bandwidth. And this is really not surprising since the optical system is fully environmentally controlled and possesses a stable pressure atmosphere. And so peak drifts are thus literally impossible. Now, except for size, Orca polychromators have few disadvantages. They are particularly powerful in the UV and the VUV spectral range, and where higher resolution is needed over a wider wavelength range. And this means better line separations in line-rich spectra, a minimization of spectral interferences, a simplified method development with line-rich matrices, and ultimately improved accuracy. The access to the wide wavelength range provides really full sensitivity for the elements. In addition, the halotens and a multiplicity of uninterfered lines are available. So a major difference between Ischel and Paschen-Runge type optical system is their behavior in terms of resolution and stray light. The diagram compares the two designs here. And while there's little difference in the 200 nanometer region, the Ischel spectrum with the Ischel spectrum, the resolution drastically worsens really above 250 nanometers, since those wavelengths can only be accessed in the lower orders. Now, with the Orca, only the first diffraction order is utilized. The resolution is mainly influenced by the focal length of the optical system and the dispersion index of the gratings used. The advantage here, also in the wavelength range above 250 nanometer, the optical resolution is high, line interferences are reduced, and the overall accuracy is improved since corrections are required at a much, much lower extent. Good example here, copper at 327 nanometer, one of the prominent emission lines for the determination of trace level concentrations here in a tungsten matrix is really a good example for the necessity of a higher resolution also in the higher wavelength range. With a resolution of 20 picometers, and that's a common value for a shell-type optical system, the surrounding peaks would almost be 3 times broader, and thus the analytical line be impossible to use. Now, another important aspect is also the overall wavelength range. Now, quite common is the range between 165 and 800 nanometers. And in this range, probably 90% of all elements have their most prominent emission lines. And so the question arises, is the VUV spectral region between 130 and 165 nanometers really relevant? Well, the spectra you see here on this slide, the comparison of a water with a tungsten matrix probably provides the answer. Unlike other spectral regions, the VUV range is rather clear from emission lines from transition elements. So emission lines presence are likely free from interference, and in addition, some elements have their only sensitive emission line in this wavelength region. Now, the halogens and the freedom from interferences have already been mentioned as the advantage of the UV and the VUV region access. In addition, 20% of all elements have their highest sensitive emission line in the range below 190 nanometers. And another 8% of all elements have their highest sensitive emission line in the region between 190 and 200 nanometers. Therefore, the UV and the VUV spectral range is important if ultimate performance is needed. So there is really a good reason or good reasons why it could be useful. The question is how to do this. Now, to access the VUV spectral range requires the right spectrometer design. And since transmission through quartz glass absorbs radiation below 170 nanometers, more transparent glasses made from magnesium fluoride need to be used. The best is really to avoid transmission optical components as far as possible. And since also reflections reduce the amount of light by about 15% per reflection, the overall number of optical components is likewise important. Another aspect is that common CCD and also CMOS detectors are not anymore sensitive in this wavelength range and need to be treated with a lumigen coating to measure this kind of light. And here the ORCA design has advantages. With no transmission optical components inside the optic and only few optical components in general, this concept provides high transparency in this wavelength range. Moreover, the use of multiple detector makes it also easy to install units optimized for this task. However, not only the optical components, but also molecular oxygen and water vapor in the atmosphere heavily absorb radiation below 180 nanometers. So the entire light path needs to be free from oxygen and water. And in the past, this was commonly achieved by evacuation of the optical system and purging of the interface and the transfer optic using argon. Now, for cost and also contamination reasons, this technique was abandoned, however. To purge the optical system is another option, but this only works to about 160 nanometers. Below this wavelength range, remaining pockets of air and water vapor cannot really be effectively replaced with the inert gas. So to solve this dilemma and provide an optic chamber free from atmospheric oxygen and water, as well as oil vapor contamination, UV Plus was developed 25 years ago. Here, a vacuum-proof chamber is first evacuated and then filled with argon to atmospheric pressure. To the chamber, a purifying circuit consisting of a membrane pump and an absorber cartridge is connected, and any ingress of oxygen and water is effectively eliminated in this way. Now, this technique is really very effective and provides excellent transparency in the wavelength range below 190 nanometers. Lifetime of the cartridges, no gas is consumed, the optical system is permanently ready for use, and also possible damage of optical components through contaminated gas is impossible. So particularly in the line-richer matrices, the UV spectral range helps with the selection of uninterfered lines. And the table you see here on this slide, which is really by no means complete, gives you an idea of where the spectral range below 180 nanometers helps to avoid interferences. Two examples: the analysis of boron in a tungsten matrix is one. And while the common emission line at 249 nanometers is heavily interfered by the matrix, the UV line at 182 nanometers is rather clear. And also for tin, the spectral range provides the analytical solution. Here, the prominent line at 189 nanometers is strongly affected, while the line in the VUV at 140 nanometers is also rather clear. So without the need for strong corrections, the accuracy of the analysis is improved. Now, one characteristic of all optical surface is their ability to scatter light. And this is undesirable light and is commonly referred to as stray light. Now, when stray light reaches the detector, it contributes to the signal noise and thus affects sensitivity. Stray light can be defined as light leaving the surface of the diffraction grating in other directions than those defined by the grating equation. Now, light can be scattered by a diffraction grating due to several causes. Irregularities in the grating coating is one, dust scratches on the surface of the grating, or irregularities in the shape of the grooves. In general, holographic gratings display lower stray light levels compared to ruled gratings. And in addition, stray light is caused by the presence of higher diffraction orders. Now, some examples here. The left picture shows an initial spectrum as recorded by the Orpheus Space Telescope. And the horizontal bright strip you see here in the middle of the spectrum is stray light, which is from two very bright oxygen emission lines at 103 nanometers produced by the Eschell grating. In contrast, as the picture on the right shows, the stray light influence, and here from a 1% calcium matrix at 189 nanometers, is much reduced using a well-designed and manufactured holographic diffraction grating. So one challenge of the ORCA design is that the spectrum is focused on a curve, and thus the installation of flat surface detectors is really not directly possible. And with a perpendicular installation on the focal curve, only a single point would be focused. A solution to this problem offers the mounting of the units above and below the focal curve and the use of aspherical mirrors, curved aspherical mirrors, to image the spectrum onto the photosensitive array. Now, the picture you see here shows how a continuous band of detectors can be realized using this technique. Now, it is well proven in the meantime, since 1999, over 100,000 CCD detectors have been installed in ICP systems alone. And currently, CMOS technology is used. Like their predecessor, those detectors do not require any sub-zero cooling, which makes stabilization quite easy. Now, the benefit from the CMOS technology is that the detectors show absolutely no blooming, not even when using a laser pointer. And this technology maintains all the attributes of the CCD technology. And in addition, smaller signals can really be detected in the vicinity of intense peaks from matrix lines. And this picture here demonstrates this nicely, while the intense line of calcium at 396 nanometers saturated. There are really no migration of charges, no influences on the flanks, and this is what you can see here on the right-hand picture. And the left picture shows exactly the same with a CCD detector, and here we can clearly see how the detector blooms, how the peak broadens, and how also the flanks are not really even. And so this area could not anymore be used for analytical purposes. Now, this picture here shows why also a high dynamic range readout is quite important. Sodium and also potassium have really only a few emission lines. And for sodium, they are two very sensitive lines, one at 588, the other at 589 nanometers, and then rather insensitive lines at 330 nanometers. And the problem is that the insensitive line at 330 nanometers only works for concentrations greater than 50 milligram per liter. So the sensitive line would need to reach up to this concentration. Now, using a classical detection system, this is really not possible. Here, the limit is typically round about 10 milligram per liter. And in contrast with a high-speed readout as used in this example, which covers 9 orders of magnitude, this is different. Using a phase interval time of 0.1 millisecond, it can read signals up to 1.2 billion counts per second. The example you see here is the line profile of sodium at 589 nanometers and a concentration of 100 milligram per liter. And what you can see here is that there are really no problems with the readout. It's still a very sharp peak, and there are also no signs of self-absorption. Okay, wrong direction. But a fast readout offers more than just standard signal acquisition. The image you see here shows time scans of different copper concentrations now at 327 nanometers and the emission line profile. Now, line ranges can be acquired with a sampling frequency here of 10 Hertz, allowing the coupling of separation techniques or sample introduction techniques with a time-dependent output. And laser ablation is one example for this, where this is required. Yeah, quite popular in research, combined with ICP-MS, a small spot laser with an automated XY stage and a magnifying camera system. It enables the spatially resolved analysis of the sample, and this is really the perfect research tool. And since only little material is vaporized with a single shot, ICP-OES is not really suitable for the determination really only for the major and the minor elements, or where elements with sensitive emission lines like calcium, magnesium, or aluminium. But laser ablation systems may also be used for bulk analysis. Laser systems with a larger spot size may ablate more material per shot. And applying a higher repetition rate and by the ablation of a larger area, the spatial information is lost, but the average concentration of the sample can perfectly be acquired. The slide here shows some examples of material possible to be analyzed using a laser system. Metals and ceramic materials are best suited and where the technique is most useful. Smaller metal parts cannot well be analyzed using spark emission spectroscopy and requires digestion for the ICP analysis. Ceramics are typically hard to digest, and for both groups of material, a larger variety of reference materials are available for calibration. And also, even though the method is not non-destructive, it is minimally invasive and parts may still be used after the test. DC-arc is another example. As a technique from the past, it was used for trace analysis of solid material. And with the advent of the MS-based techniques, GD and ICP-MS, DC-arc lost its meaning due to the higher sensitivity of those techniques. But DC-arc might still be a technique to consider, particularly for difficult to digest, powdery or granular or chip-type materials. The technique is rather easy to use, and the costs are a fraction of the costs of a mass spectrometer. The DC-arc is a separate unit which is connected to the optical emission spectrometer, and when operated in conjunction with an ICP-OES, there's no plasma operation during the analysis, but an optical fiber is plugged into the instrument's radial interface. For the analysis, sample material is weighed into a hollow graphite electrode and is placed into the DC-arc unit. A direct current arc produced between the sample and the counter electrode vaporizes the sample material over time according to its volatility, and at the same time atoms are excited to the emission of radiation, which is transferred to the optical system by the optical fiber. The DC-arc technique enables limits of detection in the lower milligram per kilogram range and RSDs in the range of 5%. And those largely depend on the grain size of the material. And as the picture shows, RSDs for materials with larger grain sizes can be decreased by milling prior to the analysis. Oh, wait a minute. Where we are. Here we are. So much like DC-arc, ETV ICP-OES shares the same benefit, and that is really no digestion required for the analysis. Again, particularly for samples requiring more complex digestion techniques, errors can be greatly reduced and time can be saved, since except for the weighing of the sample into a graphite boat, no further preparation steps are required. For the ETV, rather new is the possibility for automation. Earlier systems had to be operated manually and therefore were rather labor intense. The modern ETV systems, as used here for our tests, have an autosample tray capacity of 50 samples, and thus they are also suitable for higher sample throughput. However, there is really another important benefit of this technique. The sample is almost completely used for the analysis, which is quite different compared to the solution-based techniques. And using a reaction gas, the analytes may be separated from the matrix. And this leads to a drastic improvement of the sensitivity and hence enables the use of ICP-OES for applications previously requiring more expensive mass spectroscopic techniques. The figure here shows the calibration for small concentrations of copper and chrome in high purity graphite. The calibration functions were created with different amounts of the certified reference material. And so really excellent correlation shows a calibration with multiple data points that can really be created with little effort and cost. And sensitivity-wise, sub-ppb detection limits can be achieved using higher sample weights, in this case here 500 milligram per analysis. So to test precision, a higher purity graphite sample was analyzed using ETV ICP-OES with 5 replicate measurements. And the test shows that although solid samples are never completely homogeneous and therefore measurements cannot really be absolutely compared to a continuous solution-based analysis, really good precision values can be achieved here even at low concentrations. Now, when selecting an ICP-OES method, the first question to ask is typically about the suitable plasma observation technique, and principally there are 2 ways, axial and radial. The axial plasma observation has the advantage that the entire central channel is viewed, which improves the sensitivity for most of the elements by about a factor of 2 to 6. For the alkali and for the earth alkali elements, even greater than 10. However, this technology also suffers from stronger influences, since the entire channel is visible. All phenomena present in the excitation zone, including the plasma tail and bottom, are within the light path. Now, viewing the plasma radially, the central channel is only sampled partially. And while this provides a generally lower sensitivity, the cool top as well as the plasma bottom are blanked out, and thus matrix effects are greatly reduced. Dual side-on plasma observation has been introduced more recently. Here, in addition to a standard radial interface, light is also collected from the opposite side of the plasma and is transferred through the side-on interface into the optical system. The benefit here, an up to factor 2 sensitivity gain, while maintaining all the benefits of the vertical torch radial plasma observation technique. So this technology seems to offer really great advantages. The question is, how does it work? Now, one would think that emitted light and background are likewise increased, and thus the signal to background ratio would remain the same. However, also noise contributes to the limit of detection, and so to ensure good precision and background intensity, the background intensity must be high enough to reduce the detector noise ratio. And this means that plasma and sample induction system parameters need to be selected accordingly. Now, having more light available, more favorable condition for excitation can be selected. And this enables an increase of the signal to background ratios, lower BECs, and still better precision for the background. And as the picture shows, the sensitivity for arsenic, one of the more difficult elements for ICP-OES as an example. And using the side-on plasma observation technique, the LODs can be improved here by 50%. The improvement certainly depends on the element, and as the example of copper on this slide here demonstrates, also a gain beyond a factor of 2 is possible. Now, when compared with the single radial technique, an average improvement factor of 2 is achieved. And when compared with the axial technique, there's not really a big difference anymore. And for many routine tasks, this difference should be marginal, particularly when considering the huge benefits: the vertical torch radial interface, the drastically reduced matrix interferences, better precision and stability, certainly only a single plasma view analysis, which saves time, no contaminated interfaces, and at the end of the day, certainly also less maintenance. Now, for a single application, a decision which observation technique provides the best results can easily be made. But what if there are many? Well, to view the plasma with 2 interfaces seems to solve this dilemma. Using the radial mode, matrix effects are eliminated or are greatly reduced. The linear dynamic range can be further expanded, and still trace levels can be determined with high sensitivity using the axial interface. Without any doubt, this technology is suited for work where higher sensitivity and the elimination of matrix interferences need to be combined in one measurement, and such instruments exist, and we have them too. But what also needs to be clear is that dual view techniques are compromises, regardless whether using a horizontal or a vertical torch design. Always only one light path is direct, and the other uses a periscope. The additional optical components reduce the light throughput, certainly, and thus also the sensitivity. Also, in the UV spectral range, the performance of the direct light path cannot be reached, since the periscope optic, which is a longer light path, cannot be purged as effectively. So what to do if ultimate performance is required? And well, the answer to this question is in fact quite easy: just turn the plasma. Using the innovative multi-view technique, the plasma orientation can be altered. And to change from one into the other direction, simply the plasma torch is removed, the load coil is turned, the interface changed, and the torch reinstalled. And all of this requires about 90 seconds, and the instrument is turned from a dedicated radial into a dedicated axial instrument. Now, with the integration of the dual side-on interface, the versatility has now been further expanded, and the outcome of this is obvious. The triple interface multi-view offers analytical performance really without any compromise, whether the analytical task is the analysis of trace elements, the highly precise analysis of major compounds, the sample is a high TDS matrix, or any organic solution. Multi-view will really provide the best possible performance. So the slide here shows the technical realization of the multi-view design with dual side-on plasma observation. And in addition to the side-on interface flanged to the optical system to ensure perfect alignment, an additional argon purge tube is installed on the right-hand side using the axial plasma torch mount. At the end of this tube, a concave mirror is installed, which reflects the emitted light back through the plasma into the side-on interface. So far, so good. What are the benefits? Let's have a look at some applications, and let's start with the analysis of lithium-ion battery materials. Now, for the analysis of major, minor, and trace concentrations in cathode materials, the SpectraArcos Multiview in dual side-on and radial plasma observation mode was used for the measurement. A cross-flow nebulizer with a Scott double pass spray chamber was installed for sample deduction, and the table provides an overview of the operating conditions. And due to the higher plasma load for the analysis of trace elements run at lower dilution, a higher plasma power was applied, and the replicate read times were optimized for best performance for the relevant task. 3 materials, nickel cobalt manganese hydroxide, lithium carbonate, and lithium nickel manganese cobalt oxide were analyzed for contamination using the standard addition technique. And for the hydroxide and the NMC, 10 grams of sample were dissolved with 20 milliliters of hydrochloric and 50 milliliters of nitric acid on a hot plate. The stock solution obtained from this digestion was used to prepare a standard addition calibration with a dilution factor of 40. The stock solution for the lithium carbonate was obtained by mixing 20 grams of sample with deionized water and then slowly adding nitric acid until the solid was completely dissolved. The solution was then boiled for 1 hour to remove dissolved CO2. The stock solution obtained from this digestion was used to prepare a standard addition calibration with a dilution factor of 25. So the results obtained from the measurement is shown in this table. The sub-milligram per kilogram limits of detection relate to the original solid samples. And since the samples were measured using the standard addition technique, the LODs were calculated from 3 sigma standard deviation of the background next to the analyte peak using 10 replicate measurements of the sample. Now, the major components were analyzed using the bracketing technique. Now, bracketing is a method described in ISO standards, the ISO standard 11494 and 11495, for the analysis of platinum and palladium in precious metal alloys as the analysis of standards and samples in an alternating sequence where one low and one high standard are measured directly before and after the sample. Now, obviously, this methodology may also be applied to other materials where high accuracy is important. The combination of low standard sample high standard or high standard sample low standard is called a bracketing cycle. The bracketing method achieves very high precision and accuracy, and thus is used to determine the stoichiometric composition of materials and for the analysis of jewelry or any other compound which requires the highest accuracy. So before applying the bracketing method, an analysis using an external calibration is helpful to find the right concentrations for the low and the high bracketing standard. Now, the 2 standards next to the sample are marked as low standard and high standard. These calibration standards are then used in a second step for the exact determination of the element concentration. Now, while the determination of concentration using external calibration functions established with several standards is sufficiently accurate, or a sufficiently accurate method for many applications, balances out the errors of the standards used as well as non-linearities and drift over time, and thus, even when small, has a negative effect on the accuracy of the analysis. And in order to eliminate these errors, achieve the highest precision and accuracy for the determination of major compounds, the bracketing method is used. The principle of a bracketing method is the alternating measurement of one sample and 2 standards. First, the low standard is measured, then the sample, and then the high standard. These 3 measurements can be counted as one bracketing cycle. After this, the sample is measured again, followed by the second measurement of the low standard, which finishes the second bracketing cycle. The sequence is typically continued until 5 bracketing cycles are completed. The analyte concentration of each sample measurement is established using the corresponding low and high standard measurement of each bracketing cycle as a calibration function. This function is defined by the corrected intensity ratios of each measurement and the exact amount of analyte inside the standards. Highest accuracy using this method can be achieved if also the exact amount of the internal standard solution added to all solution is considered. Finally, the analyte concentration of the sample can be calculated using the mean concentration value of all sample measurements and the sample weight. Now, for the test, 3 NMC samples were prepared in duplicate for analysis by dissolving approximately 100 milligram weight to the nearest 0.1 milligram in 10 milliliter of aqua regia and heating to 80 degrees Celsius for 3 hours, resulting in a complete dissolution of the materials and removal of nitrogen oxides in the solution. After cooling down, the digested samples were transferred to 500 milliliter volumetric flasks. So the values highlighted on these pictures demonstrate that perfect results can be achieved using the bracketing techniques. The samples were analyzed using the bracketing technique with 3 cycles. And the table lists the mass concentration, the molar concentrations, and the nickel normalized stoichiometry and the RSD values obtained from those measurements. The results really show excellent agreement of the duplicate preparations of each sample and a very good precision of the measurements. Molar ratios of nickel, manganese, and cobalt very, very close to the expected values were obtained. Now, ICP-OES is also a good method for the elemental analysis of petrochemicals. In diesel fuel, particularly phosphorus and the alkali elements, sodium and potassium, as well as the earth alkali elements, magnesium and calcium to a lesser extent, can negatively affect the catalyzers within the exhaust gas treatment system. And in addition, sodium, zinc, and copper can yield carbonization in the fuel injection system, as well as deposits in the combustion chamber, while in general, metals are responsible for the formation of ash, which may potentially block the particle filter. So a control of trace metals is important for this reason. And to cater for those challenges, the European standard 16476 has been developed. Another method for the analysis of diesel fuel is the ASTM method D7111. Now, for the analysis of dual side-on plasma observation was used. Plasma parameters reflecting the higher load were selected, and the calibrations were prepared by a preparation of a stock standard using multi and single element standards and kerosene as a diluent. To cater for viscosity differences, as samples with different biodiesel content might need to be analyzed, yttrium was used here as an internal standard. Limits of detection in diesel fuel in the microgram per kilogram range, well below the requirements, were obtained for sodium and potassium, the earth alkali elements, as well as for the metals and the non-metals such as phosphorus, sulfur, and chlorine, which can be determined in addition without the need to employ other analytical techniques. Now, the same methodology may also be applied for other petrochemical products. Kerosene as a diluent works equally well for fresh and used lube oils as well as for gasoline. So to confirm the accuracy of the calibration, a commercially available diesel sample was spiked with 12 milligram per kilogram chlorine, 10 milligram per kilogram sulfur, and 0.4 milligram per kilogram for the other elements. And the comparison of the results with the reference values really shows a good agreement for all elements. Now, for the analysis of AUS32, ICP-OES with dual side-on observation is also a good choice. And the analysis of urea solutions is really a perfect example. The quality of the urea solution is regulated through the ISO standard 22241-1, which sets contamination limits for a range of metals and alkali elements. Now, following the latest revision of the standard for the analysis of AUS32 using radial ICP-OES, a solution of 32.5% was prepared. The solution was diluted 1:1, spiked with multi-element standards and acidified with 5% nitric acid. Samples were diluted in the same way. Plasma parameters were optimized for the higher matrix with a higher plasma power, and increased auxiliary flow was also used to prevent carbon deposition on the injector. And again, a Nordimer cyclonic sample induction was used here for simplicity reasons. Now, the limits of detection achieved agree well with the requirements to control impurity limits at a 200 to 500 microgram per kilogram level. The difficulty is the carbon content in the samples and carbon molecular interferences caused by this fact. In addition, the acidified aqueous urea solution will decompose to carbon dioxide and ammonia, and this matrix change, even though small, continuously changes the structure of the carbon background, and an effective way to model the background is needed to compensate for this. The picture on the slide shows the peak region of phosphorus at 177 nanometers with the structured background and how smart background correction is capable to model the background, displayed here as the green line. Now let me conclude. What makes ICP-OES the perfect research tool? Now, depending on the instrument design, I would say performance and flexibility. Multiview closes the gap where for different analytical tasks, dedicated observation is preferred, offering all advantages of both observation techniques without the disadvantages of a classical dual view system. Ultimate analytical performance is obtained. The triple interface configuration includes dual side-on observation now, which provides an up to factor 2 higher sensitivity. With its wide wavelength range, the Orca polychromator encompasses the complete ICP-OES elemental scope, including the analysis of the halogens. A uniform high resolution ensures that also in line-richer matrices, interferences are minimized, fewer corrections are required, and the accuracy is improved. And a CMOS detection system eliminates blooming and enables the detection of smaller signals, even in the vicinity of intense peaks from matrix elements. And with a maximum rate of 1.2 billion counts per second, concentrations really from sub-ppb to % can be detected. And in addition, a fast readout enables transient data acquisition with a sampling frequency of 10 Hertz. And with this, I'm at the end of my talk. I thank you very much for your attention. And I believe and I hope we still have got some time for questions. And for any you might have, please use the chat function.
Thank you, sir, for such an informative talk on ICP-AES. We have some questions lined up today. So our first question is, we want to analyze 3% acetic acid and 50% ethanol. Water-based sample for heavy metal analysis in 10 ppb level. Is it possible to directly analyze using different nebulizer like ultrasonic nebulizer?
For 50% ethanol, an ultrasonic nebulizer is principally not required. Yeah? That can be done with a normal nebulization system, at least with the systems we built. We employ a generator system which is extremely high powered, up to 2000 watt plasma power can be adjusted. And for that reason, basically and principally, this kind of solution can be nebulized directly and introduced into the plasma. What is possible, what can be done if some further optimization is preferred, is then to use a slightly cooled spray chamber. And for this, today, Peltier cooled spray chamber systems are available. So by chilling the chamber to, let's say, around about 0 degrees Celsius, we have got, let's say, a bit of a lower intake of sample into the plasma, and that gives us some more possibilities to optimize the system. Now, there was another question regarding the concentrations which need to be analyzed. Can you please repeat that, because I don't see that here?
Same question, sir.
Yeah, there was a second note regarding the concentrations. Where's my mouse?
Okay. We want to analyze 3% acetic acid and 50% ethanol water-based samples for heavy metal analysis in 10 ppb level. Is it possible to directly analyze using a different nebulizer like ultrasonic nebulizer?
Yeah, 10 ppb is in an organic matrix. 10 ppb is round about the concentration you are still able to analyze. So here, that is really something which needs to be tried, whether a normal pneumatic system will suffice. Certainly using ultrasonic nebulization is principally possible as well. However, in this case, a membrane desolvator would need to be used. Now, I recall that those systems have been available in the past, but more recently, I think they are not available anymore. So here, the best possibility at the moment is to use really a pneumatic system and either do a direct analysis, which works pretty well, or maybe chill it down a little so that there are some more possibilities to optimize the sample intake.
Okay, sir. Sir, another question. What is the method for sample preparation? Does it changes by changing the nature of metal? If I want to analyze a material containing transition metal, then what would be the method for sample preparation? So, can I
Well,
repeat?
typically metals dissolve fairly well in acids, and either hydrochloric, nitric, or aquaregia are, let's say, are a good guess for the dissolution of metals. But it depends. I mean, really, one needs to look at the type of metal, at the type of alloy, and one needs to also look at the elements which need to be analyzed. There is really a great variety of dissolution methods available depending on the type of metal, and also time-wise, there is a larger difference. While for instance, copper dissolves fairly well and very quickly in nitric acid. Think of a platinum or platinum iridium alloy, which we just did in our application lab. It took us about 3 days to digest.
Sir, next question. For alkali metal estimation, which plasma is best, axial or radial?
Axial plasma observation will provide you the higher sensitivity, so really sub ppb limits of detection. But there's one problem with axial plasma observation, since the alkali elements are easily ionizable. If you've got varying contents of the alkali elements in your solution, then you have to deal with the easy ionizable element effect. And the easy ionizable effect means that basically that with the presence of another alkali element in your sample, for the same concentration, you will read higher signals because you get basically an enhancement in the excitation conditions in the plasma. You can do something about it, and what typically is done if axial plasma observation needs to be used for this kind of task is to employ a buffer. And the ionization buffer, which is typically used, is cesium at higher concentration levels, around about 2,000 to 3,000 ppm added to the solution. And that kind of equalizes the samples, and so the EIE effect is reduced. Not using axial plasma observation, but radial plasma observation has the benefit that there is no EIE effect. So the EIE effect is very, very strongly reduced because the relevant sections of the plasma are not transferred into the optical system. But with a disadvantage that the radial techniques are not quite as sensitive compared to the axial technique. And here, also the dual side-on technique does not improve it to the same level. With the DSOI technique, we get about also maybe a factor 3-4 improvement for the alkali elements, but the comparison between axial and radial plasma observation is really that we see improvement factors which are greater than 10. So if somebody really wants to do trace analytical work, there's no other way but to do that with axial plasma observation.
So one more question. Is it necessary to dry out the HNO3 or aqua regia that we use for digestion, or we can keep some volume and dilute it?
Can you please repeat? I haven't quite understood it. Can you please repeat the question?
Is it necessary to dry out the aqua regia that we use for digestion, or we can keep some volume and dilute it?
To dry out?
It is necessary to dry out nitric acid or aqua regia that we use for digestion, sample preparation, or we can keep some volume and dilute it.
I don't quite understand dry out, what is meant with that, but yeah, I mean you can use concentrated nitric acid and dilute it. Well, aqua regia, I mean you should not keep, but you should add it to the sample individually. You should add the acids individually to the samples as needed.
So one more question. How to digest the sample containing some heavy elements like niobium, zircon, etc. Niobium, zirconium, etc. How to digest the sample containing some heavy elements like
yeah. I mean, again, I mean that depends on the matrix and in which those elements are present. And you might need to employ techniques using a variety of acids. For example, if we talk about the determination of those elements in geochemical samples, rocks, for example, then it is typically a 4-acid digest, which is performed 4-acid digest using nitric, hydrochloric acid, HF, and perchloric acid as well. In some cases, it is also not the digestion using acids, but it is fusion, which is used, fusion using lithium or sodium tetraborate, and then the dissolution of the fused material in an acid. As I said, dissolution always depends on the matrix because you need to not only, well, okay, that's another possibility is also to leach the sample out to leach the elements out of a sample and then filter the sample and analyze the filtrate. But as soon as you like to and want to digest the sample completely, it is always the matrix which is important.
So last question. How do anyone take into account uncertainty associated with two different instruments used for measuring metals, that is ICP-OES and ICP-MS?
Again, please.
How do anyone take into account uncertainty associated with two different instruments used for measuring metals, that is ICP-AES or ICP-MS?
Well, basically, it comes down to the development of a method. It comes down to a validation of the method, and then a comparison of the two methods. And you will find different results not only between ICP-OES and ICP-MS, but also when this is what is regularly done. Round robin tests exactly work in this way, that several instruments are used to analyze a single sample, and there each instrument uses a validated method for the analysis of one sample, and from there you can calculate an uncertainty. And if you do this multiple times on different elements and you evaluate the results, you will then are able to evaluate an overall uncertainty. So basically, what you need to do is to judge whether a result is still within the uncertainty range or not, is to use a method which has been tested using a round robin test. So ISO methods and ASTM methods, they do offer that and do give data about small and capital R's, and from there you can see whether what kind of uncertainty you can expect when using methods to analyze material.
So one more question is there. If Si or SiO2 is present in sample, only platinum nebulizer is suitable or quartz can be also be used.
Where do we have that? When S? Can you please repeat it?
Yes, sir. If silicon is present in sample, only platinum nebulizer is suitable or quartz can be also be used.
You can use quartz to analyze silicon. That is possible. Depends, however, on the concentrations you need to analyze. If you need to analyze trace levels, really trace levels for silicon, then the use of a silicon-based material obviously is problematic, and you will need to replace the silicon bearing parts with something else, and then it is helpful to use, for example, a spray chamber which is manufactured from a plastic material, Teflon, for example. Same applies for the nebulizer, and also the same applies for the injector tube, which is used in the plasma torch, which is then typically be made either from a ceramic material. Aluminium oxide is typically used, or the other option is to use torches or torch components made from sapphire, which is, however, a relatively expensive option.
So one more question is there. How to choose
PTFE or
wavelength?
platinum, yeah.
How to choose wavelength for the transition metals for measurement?
There are wavelength tables in a typical ICP-OES software, and there are so-called prominent ICP lines, and those prominent ICP emission lines, they are highlighted. ICP-OES is a technique which is done for a longer time, started in 1978, and so by now, let's say, emission lines which work well, they are quite known. And so in every software, in every wavelength table, there is a so-called list of priority lines, and those are the lines to first turn to. In addition, a modern software checks whether there are interferences or possible interferences with other lines. By the lines you select, it checks, and also by the matrix element select, it checks whether there are any possible interferences. And also those would be highlighted, and those would need to be checked if an interference is really present. So in case this is the case, then the next step would be to just select another emission line, and you would first use another of the prominent emission lines. And ultimately, when this is not possible anymore, then it's really like you have to go through the wavelength table and try and find another suitable line which is maybe not interfered. For some applications, this is not possible. Then there's only one other possibility, and that is to correct for interferences.
Thank you, sir, for answering all our questions.
Very welcome.
One important note, a link for the feedback form is shared in the chat box section. Do fill the form. Your valuable inputs are important to us.
So on behalf of staff IIT Bombay, I thank Speaker Olaf Sues, Spectroanalytical Instruments, Germany, for his valuable talk and for time this one. I also thanks Professor Suparna Mukherjee, Head SAF, for their valuable suggestion and for conducting this webinar. And I also thanks the participants who has make this event successful. I also thanks Mr. Anthony Thomas and Mr. Milind Pathare from Spectroanalytical India for conducting this webinar. I also thanks our team, Ms. Vinita, Reshma, Meenal, Princy, Nidhi, for conducting this webinar successful. If anyone has any doubts or they want to connect us, so these are our email address and contact details. You can mail us, and we will put the recording of this webinar soon on our YouTube channel of SAF IIT Bombay. So if you have any doubt, you can contact us the mail address given. Thank you for your participation.